Okay, I think everybody has left congregate. Yes, everybody but one person. That's okay. Good. So, welcome back. Welcome to session 2. And I am thrilled and excited to introduce our first keynote speaker, Carl Wieman, an exceptional person who is one of the very few people who is distinguished both in physics research and in physics education research. And I've known Carl for, how long have we known each other, Carl? I think it was back 20 years or so when
not even close, Eric. It's got to be over 30.
Really? But it's, oh, okay. Time flies, I guess.
We were brand new assistant professors when we.
Yeah, well, probably that's right. Well, Carl is currently a professor at Stanford University, where he holds appointments both in physics and in the School of Education. He has enough awards for me to fill the entire session by just enumerating them. Let me just mention 2, the Nobel Prize, which he won in 2001, and as well as the Oersted Medal, which he was awarded by the American Association of Physics Teachers for his excellence in teaching and in education research. I already heard someone or several people mention the FETs earlier today. Well, that is one of the activities that Carr was very actively involved in the early 2000s when he was at the University of Colorado in Boulder. Carl, I am so pleased. I know you're incredibly busy, but I'm so pleased that you have taken the time to address us here. So without further ado, I'm handing it over to you.
Okay, well, thank you. It's a pleasure to see all of you and eager faces. We're thinking about how to teach better. What I'm going to talk about today, the particular focus, is what I call a scientific approach to physics education. I think, lots of you have heard these clever methods and use of technology and different techniques and so on. But what I want to do is try and take a bit higher level approach to this and talk about not just what these techniques are and data on why they work, but how one can think about it like we do physics, of understanding, particularly from the basic learning science, brain science perspective, not just that they work, but why they work and the underlying principles behind them. Because I think that just like in doing science, it's not enough to know the steps to follow. You really have to understand the underlying concepts before you can take full value and appreciation and use of it. And so that's going to be the general idea that I'm going to follow here. But like happens so many times these days, the headlines this morning sort of pulled me away from my original talk a bit. So I want to start actually focusing a little bit more general on the basic issue. What's the goal of education, really, and particularly the goal of science education? And I think it's never, in our society, it's never been clearer and more important what that has to be. It's really about having our learners, the students, the future citizens, make better decisions ultimately. And that's really what matters. And you can see, and what I mean by that is that and I'll talk a little bit more later about this when we get deeper into scientific problem solving, studying, but it really means that there's a set of knowledge and processes that scientists, and including in physics, that they've learned, tested, and used to see how to make decisions in situations in which there's limited knowledge. And you think about that, it's we don't pay enough attention to that. But when there is uncertainty, when you aren't just following a bunch of clear steps because everything's well defined, it's how we make intelligent science-based decisions, and how to make those better, whether it's, in a job, in a workforce, solving complex problems, or right now, and it's so important today, in our own personal and public policy choices. Um, and so, I just want to stress that any teacher really, it's really critical, especially these days, to keep that in the back of your mind, is that you want your students to walk out of that classroom able to face, the uncertainties of the world, and you give them better tools, better processes, better ways to make decisions. Um, and using science to do that. Um, Now, of course, we see this every day. What inspired this was just reading about the governors of all the states and how they're trying to make decisions about, the pandemic, and how essentially terrible they are. They're just totally unsuited for this, both in their scientific competence, but also in their really the whole process of making decisions. So, but when we focus down to what you're accountable for and you're teaching, oftentimes, at the course and program levels, you ought to be thinking about, okay, in some relevant context, where relevant something the student, is going to encounter in their daily life, in their future careers, etc. Um, can they use the knowledge and reasoning of the discipline, and for this case, physics, but of course it's broader to science, to make decisions where it's not just following a set of procedural steps? And that's what you should be asking yourself, and that's what, if you're providing, and that's what you should be, trying to evaluate your programs. Now, I stress this because if you look at all of our, everything about high stakes testing and so on, it never involves making decisions, right? I mean, it involves memorizing. If you're given this term, can you define it? If you're given this very artificial, perfectly laid out situation, can you follow a set of procedures? Or can the student follow a set of procedures? That's not useful at all. It's when you throw them into real complexities, can they realize, well, no, that's just not going to work because that's going to violate conservation of energy, or this design of automobile is just fundamentally going to be less effective. And there are all those situations, but we need to be thinking about conveying them and having students learn them. So, okay, so the rest of my talk, which I'll probably cut off because I've been blethering too long on this, is what the research tells us on how to have students learn this more effectively. And I'll give you a shocking, the bottom line is kind of a shock. Turns out, well, what all the research says is if you have people practicing making decisions with feedback, they get a lot better at it than if you just tell them what they should have decided, okay? And you can sort of condense all of research results down into that, but I'll elaborate on that a little more. So I'm going to talk a little about the basic principles, and then applying those principles, a little of the research that we've seen, and then what's behind some of that research. Before I jump into this, though, for whatever reason, almost always physics teachers want to know, how did I ever get started thinking about this? And it is kind of useful to explain because it gives you the orientation I'm coming from to education and physics teaching, which is that it actually didn't start from my working with teaching physics classes. It came from my not physics education, but AMO physics research, blasting atoms with lasers, and seeing this phenomena that these graduate students would come into work in my lab, many years of spectacular success in coursework, and then they were really seemed to be pretty clueless about how to actually do physics in the way that we were doing in the lab. But it wasn't that they were fundamentally incapable, because they would quickly learn to do this over a couple of years working in that. And so, if nothing else, I'm kind of a curious person. And so I decided, this isn't just a funny thing with individuals. There's some fundamental question here about how people learn to be experts. And so I started seriously looking into that some 30 years ago. Um, and digging into the research on how people learn, particularly how they learn physics. And Eric and others had already been working on that. So that gave me a good starting point. But once I looked at that literature, I could both understand this made sense. There wasn't a puzzle here. And it also made me realize there were a lot more effective ways to teach than what most students were getting. And then it got me started actually in this whole field. And so, now many years and many publications later, I'm still focused particularly on the idea of what makes up expertise, what makes up, let's call it, scientific thinking and problem solving, and how's the best way to teach and learn that. So, okay, so jumping ahead now, turns out this has been studied, particularly in physics, for quite a while, kind of been leading the efforts in this. But in the last couple of decades, there's been work from cognitive psychology and brain research that's also couples in nicely to explain and support the how people learn, what I'll say, and how best ways to teach, I'll say, complex thinking, which is, thinking like a physicist. And I'm going to start with the most fundamental basic result, and it's a fundamentally different paradigm for thinking about learning than what's used or what's applied in basically all university science, pretty much, and frankly, high schools as well, although they're not quite as bad. But and so this is sort of the most important thing to take away is the current model, which is historical, is that these different brains come into the classroom and they get immersed in knowledge, and that knowledge soaks into different amounts depending on what the condition of that brain was originally. So this is the basic model one thinks about learning and education. Then it's kind of natural that then universities, their main focus in trying to improve education is, okay, trying to figure out optimize the contents of that knowledge soup, what the curriculum is, which topics come in which order. And selecting the best brains, the brains that is going to soak into the best. And then finally, when it doesn't work as well as they think, blaming K-12 on anything that goes wrong. But research gives us a profoundly different view for thinking about learning, particularly this complex learning. And that is that the brains aren't all that different when they start, but they're highly changeable. And that's the critical difference, is the education process is actually transforming. It's quite literally rewiring those brains, hooking up the neurons in different ways. And it's really within that rewired brain, rewired neurons, that these capabilities lie. And so it's not about giving knowledge to an existing brain, it's really about changing that brain. And that those changes come about only because in response to that brain having to exercise strenuously. So really thinking intently about things for a long period of time causes neurons to hook up in different ways that are better at solving the problems they're given to solve. And we can, in fact, not just, this isn't just hypothetical. Now with modern brain imaging, you can actually see this. And so I like this image here where it's showing two functional MRI images, one of two people processing, interpreting an X-ray image, okay? One of these on the right is a medical student who's just learning about how to do on this. On the left is a highly expert radiologist. And you can see how their brains get activated in completely different ways. And that's just because, okay, they've been wired up differently. To the one on the left is just a lot better. Now, the other thing I want to stress before leaving this is that the teaching methods really dominate the impact on the brain compared to the topic coverage and the particular content, because it doesn't really, you can cover any possible content in different ways. And some of those ways, the brain just kind of drifts along and doesn't have to do any work. Other ways, you can really have to strenuously think, solve, practice making decisions. That's the thing that causes it to develop and improve. Okay, so that's the big picture. Now let me kind of jump into giving you some examples of just some quick examples. You've maybe already seen them, but of why do we believe this? Some of the research that actually supports these basic principles. And there's, I don't know how familiar you are with physics education research, but there's many hundreds of different experiments looking at different things. But if you sort of filter those down to what's the essence of the ones that really show the most significant impacts and differences of teaching methods, they're ones that really test on how well students can make decisions like experts, okay? So if you think about these concepts inventories and force motion inventories and so on, what's different about them is that fundamentally you give students some simple real-world scenario, more realistic real-world scenario, and they have to decide what's going to actually apply and what's going to actually happen there, compared to giving them a perfectly laid out problem and they just follow procedures. And some of Eric's works very nicely showing how students can follow very complex procedures to predict things, but then they, in simple real world situations, have no way at all to decide what's actually going to basically be happening. So those are the basic idea. And then one compares the results with one uses the sort of traditional lecture approach, which is really based on given a well-defined situation, telling the students what they should do and then have them practice following that procedure, as opposed to the research-based instruction, or all these different ways that they have to actually make decisions and process in more active ways. So, okay, so I'll give you one example that has gotten a certain amount of attention when experiment we were involved in. This is doing this kind of experiment in a big introductory first year physics class with two sections of 250 students each, and carefully measured that they were identical in all respects. And the control session was somebody who giving a basically traditional lecture, but somebody who was a highly rated, faculty by the student evaluations, highly rated lecturer. And then the experimental section was someone who was a relatively new PhD, but trained in these research-based methods of teaching. And so, and then they agreed to cover the same amount of material and the same amount of class time. And then they gave both sections the same surprise test to see how well they learned. Now, I want to emphasize this, unlike most education research where they look at the learning that takes place over the entire course and involves homework and exams and so on, and that's of course a completely reasonable thing to study. This was focused on just what they learned just in the classroom, just from the lectures, and the timing was all set up to measure that. So that's just as a research question. So the
Can I
experiment,
can I
yeah.
can I alert you to a question in the chat from Veronica Monti, who is saying something that I think might be good not to postpone till the end, asking to elaborate more on your statement of taking better decisions with limited information for student success. What exactly you mean by that?
What I mean by that is I'll go into a lot of detail about what those decisions are, but let me just give you a specific. I'll talk here about the experimental, the way the experimental course went, and try and pull out so you can see where they're making decisions during what we're having them do, and then I'll go more in depth about that later on. But just to capture some of these decisions, I mean, it's you take any real world problem that somebody's faced with, you have to decide, what concepts actually apply there, what physics concepts will apply, what information you need to actually make the best conclusion, what the credibility of what information you get is, and so on. So all of those things are some of the kind of decisions that one has to make in doing any real question or facing anything you're having to do in your life. And the issue about limited information is one that I had sort of not appreciated until we started studying how experts solve problems. And that is that, there's really two different kinds of actions you have to take. One is you're given all the information and you just you just look it up, or you plug it into a computer. And those aren't really very useful because, that's all automatic. It's all the millions of places in real life where we don't know everything. We don't know exactly what's going to happen. We're just trying to make the best possible predictions. So, okay, so back to this study in the experimental class, they have this is going to look very familiar, hopefully, to a lot of you. They have a short reading, pre-class reading, gives them sort of basic facts and terminology, so I don't have to spend class time on that. And then the class doesn't start with telling them a bunch of stuff. It starts with a question. This was a familiar one, that when you close that switch, what's happening to the brightness of that bulb number 2? And then this was a number of years ago, so we're still using clickers then. So the individual student all has to answer. And that's really important because it's this idea of not just posing something, but the brain has to process it enough to commit to an answer that the students are at some level accountable for. That makes it work harder. And so that's kind of one thinks, oh, it's kind of clickers are kind of trivial thing to check understanding. No, it's actually much more deeper than that. They and similar things are ways to force the brain to work harder to be better prepared to learn. Okay, then, following Eric's peer instruction, they answer the question, but they don't know, what's right or wrong. They then have to talk to each other in small groups and re-vote. And I want to emphasize a couple of things here, that there's not just the value of talking to each other, which is a kind of unique cognitive aspects I'll come back to later, but this is also really valuable from the point of view of, I stressed at the beginning, the key aspects of practicing with guiding feedback that tells you not just you did right or wrong, but how to do better. And in this case, oftentimes I see teachers overlooking the enormous value that comes from listening in on those conversations. So you get a much better understanding of what's going on in the students' brains so you can teach more effectively. Okay, so then they get a demonstration of the result and then a follow-up discussion and feedback from the instructor again, I stress the value of addressing really the student thinking in a very explicit way. So not just what's the right answer, but more importantly, when their thinking's wrong, what's wrong about it, they can understand what's wrong and how to change it and then go forward. One of the things I've learned in my cognitive psychology friends is that it's that kind of so-called, negative, although in many ways it's more positive feedback, that actually is where most of the learning takes place, is when you learn not that you did something right, but you can understand why you're thinking incorrectly about it. So, okay. Now, getting back to the decisions part, think about how they're making decisions, practicing making physicist-like decisions during this process, okay? They're faced with this problem of light bulbs and batteries, and they've got to think about, we didn't tell them how to do that. They've got to think about what their concept of electricity is, how it's going to apply here. They've, what their conceptual model is. And then they also have to make decisions about when they're talking with fellow students. Those students are proposing, conceptual models, and they've got to critique those models. They've got to decide how to best justify their models to fellow students. And so that's the kind of, if you think about it, that's the kind of decisions they're having to make and processing they're having to make. But they're also getting feedback on their thinking, both from the discussions with other students, from the instructor, and comparing with what happened. So, okay, so that's a very long, winded way of explaining what happened in the experimental section compared to in the control, where they're just being told all these things about electricity and Ohm's law. And so when one then looks at the comparison of the two sections on this surprise quiz that came right after the 1 week of lectures on this, you can see here the histogram of scores versus number, and there's quite a profound difference, obviously, with the experimental section being much higher. Actually, on this particular test, random guessing would give one about 3. And so you really have to look at this as kind of how far above 3 are the different results. And when you recognize that, you can see just how tiny the amount of learning is from a lecture like this. And, people find this hard to believe, but these are easy experiments to duplicate. Before I started in this field, I was doing a test like this in my own class. And so, it's just painfully clear. If you actually measure what students walk out of a lecture with, it's very little. It's also important to appreciate that here, as in other studies, it's not just a select group of the students that improve. You can see the entire distribution has moved up. So this is really, goes to the heart of my point of, we're really looking at how the brain learns, and all these students have human brains. And so it really is beneficial to all of them, this kind of more active teaching. Okay, this is just to throw in that if you look at other things like drop and failure rates and in other subjects like computer science, the same kind of changes in teaching, again here with the same instructors, give profound improvements. So now at UC San Diego, for example, in their introductory computer science courses, they have about 1/3 the drop and failure rates they used to before. And the only thing that's happened is the instructors have adopted these better research-based teaching methods. Okay, so how am I doing time-wise? Yeah. So there's lots and lots of studies showing this. They always show it works great. Since most of you are K-12 teachers, I did want to say a little about that. And because almost all the research is from higher education, particularly universities. And the first point is just the research is harder at the K-12 level. And I don't need to tell you that you just have, and it's just because there's a lot more confounding variables that you have to deal with in the classroom every day than we do where we go to a nice selected population of, elite university students. And so that just makes the research harder. And so the results, have bigger uncertainties. But to the extent the research is comparable, you see the same effects. And more importantly, I think we have enough data now from kind of the learning sciences to really be quite confident that at least at the high school level, the ideas are going to apply in very, very much the same way. Okay, so I'm going to now sort of jump to the big picture of summarizing all the research that we know on teaching and learning, at least in STEM, and what the research shows as really important factors in the student learning outcomes. And this is kind of my big concept map, and with the key idea being that it's, the essential element is the practicing making decisions with good feedback. But then we know a lot of things have to go into the design of those practice activities and the implementation in the classroom. And I don't have time to talk about those now, but I'll just kind of point out what matters, okay? So there's the disciplinary expertise. It's what is involved in making the appropriate physics decisions, using the appropriate physics knowledge to make those decisions. So that's where it brings in what really thinking like a physicist is about. And then there's a bunch of things. These have to be matched to the students, and there's a student variation in terms of their prior knowledge and experience, their motivation, and so on. Those are critical in terms of designing things that will work. And then there's some basic constraints about the brain. And then there's, a fair amount of research on implementation in the classroom. What kind of questions and deliverables seem to work best? And also the optimum way to use and the values of social learning. So I'm going to just pick out a couple of these that I thought you might find interesting, and then finish here. So, but what I will say is, I believe that we're kind of at a major turning point in terms of thinking about education, in that really for the first time in history, we can really think about expertise in teaching, where we have a research base, sort of like where medicine was in the mid-1800s. You've got a research base that doesn't know. There's some basic principles here. You use those, you apply those, you get better outcomes, and you get it consistently, and it's not just an individual, choice kind of thing. Okay, so disciplinary expertise. This gets back to some of these decisions. And so just put in a quick plug. We've been studying now for the last couple of years, my research group, how expert scientists, and not special experts, just highly competent faculty members or leaders and engineers at major companies, how they solve problems, day-to-day sort of authentic problems they're faced with. And we find all of these, their process is really governed by making a set of decisions with limited information, and the way they call on information to make those kind of decisions. What's really been startling is to find out it's the same set of 29 decisions across all the fields of science, all the fields of engineering. We haven't looked at all of them, but we looked at a lot. We've done kind of 100 or so cognitive problem-solving interviews, and certain areas of medicine, particularly diagnosis. And I want to emphasize, the decisions are the same. They're decisions like, what information do I need? You know, when I have information, what conclusions can I draw from it? Those are general across the field. But of course, actually making the decision brings in all kinds of specific disciplinary information, knowledge. So I don't mean to say you can teach somebody to be a good problem solver in physics and they'll be able to do everything else. But this makes it clear there's a discipline independent aspect of making decisions, and then discipline specific aspects of what knowledge is needed to make those decisions. And so, but it's a very helpful way to think about actually teaching and assessment of learning. And so we're in the middle of trying to get all this published, but it's, you basically, you know, there's certain sets of decisions about laying out goals, framing the problem, planning, you know, decomposing it into pieces, and then deciding what information you need, collecting it, how to interpret, etc. But I'm going to focus that down just to what you can be thinking about when you're giving students physics problems. These are the kind of decisions that to useful learning involves. It's when faced with a new scenario, it's, you know, what concepts or mental models are going to actually be applicable to that situation, what information's relevant, irrelevant, needed to solve the problem, what approximations are appropriate, and then, you know, what's a set of potential solutions to pursue, and then eventually you get down through the 26 to, you know, if you got an answer, do these conclusions make sense? Now, I want to stress these in particular, because if you think about, like I have, and you've gone back and you look at the normal physics textbook and all the problems they list in there, and the usual exams, all of these decisions are removed. Okay, they tell you, you know, you neglect air resistance. You know, the structure of the problem is such that, well, this is a conservation of energy problem you're supposed to be solving, you know, in this part. And they give exactly the information that's needed and no other information, okay? That's fine for a physics textbook problem, but boy, you can't find any real world problem that ever looks like that. So that's all the things students can solve that certainly have no value to them in their actual, you know, real life. And so that this is kind of my point of thinking about what you're expecting. And, you know, people look at this who teachers think, oh, it'd be impossible to ask those things of students, you know, that'd be really unfair. No, it's only unfair if they never see it before an exam. If it's part of what you teach them to learn, they have the capabilities and they'll go out of your classroom with far better capabilities than would have otherwise. Okay, so I'm going to just finish up here with one last thing about brain constraints, because this is something a lot of people don't know about, but it's very well studied and fundamental from cognitive psychology, and it's useful for teachers to learn. It turns out, if you think, you know, fundamentally, memory is critical in this. We want people to remember and be able to use those things that they remember, okay? And so a sort of simple view of memory is it's got two parts. It's got the long-term memory, and that's what most of us think about as memory. Big capacity, lasts for a long time. But it has this buffer, this short-term working memory, it's called. And that's really the stuff that your brain pays attention to on a short time scale. Not just your brain, but it turns out every brain that's going down to even pretty basic organisms has this kind of working memory buffer. And unlike the long-term memory, it's got this really small capacity. You may have heard about sort of, you know, 5 or 7 items people can remember. That's really the limits on which a typical human brain can pay attention to. And it turns out that that's really critical, because stuff has to go through this working memory buffer to get into the long-term memory. And so because this is so limited, if you're trying to teach students things, you want them to get it, get it in through here into long-term memory, but something comes in and it uses up some of that short-term working memory, it's gone. So it never is going to make it into long-term memory. And so you have to just look at all the different things that can fill up this working memory, and those will really hurt learning unless they're essential to what you're trying students to learn. And so so there really anything that it takes attention, because that takes process and learning. And so for example, if your students are splitting their attention to checking their phones or doing anything in class, that's using up this critical limited working memory. And what one sees when you measure it, when you split attention like that, learning just plummets. So anything you can do to keep them focused on the task, not splitting attention, is going to make a big, big difference in their learning. And it turns out some of these things are kind of obvious. You'd think to avoid, like, jargon and complicated picture images that they have to process. But what some of them aren't so obvious and kind of shocking to teachers, that funny joke that gets everybody's attention and they laugh at, okay, they may pay attention to it, but that attention itself, unless it's completely, that joke is intimately involved with the learning, the physics you want to be thinking about, it's just kicked out a bunch of physics you want to learn. And so they actually, talking about seductive details, they actually will learn less when you have those things. Okay, so then that's one of the key things to think about, this working memory and how important it is that you think about managing its demands on it during your teaching. The one other thing that's well established but not thought about much in teaching is a particular property of the long-term memory. We want stuff in there and we want to get it back out. It turns out that the biggest problem is not getting things into long-term memory. It's able to recall them appropriately when you need them. And, if you're taught, pretty much every teacher knows you can have things, you'll have students work on it, they seem to know it, they do well on tests and problems, but gee, you come back 3 weeks later and they get it all mangled and they're not thinking about the right thing at all. And the problem there is the problem with interference and recall. So I got this nice block of stuff in my long-term memory, and I built up these neuron pathways that say, when I'm doing this kind of problem, run down this neuron to grab this piece of knowledge. Unfortunately, when I start learning new stuff, then I got new neuron connections coming in there, and they cause a lot of interference with me finding my way to the right knowledge. And so this interference of new learning, interfering with people's recall of old ideas, is actually a big problem with long-term attention. And it's not that hard a problem to fix. That's why I'm stressing it. You just have to have, the brain has to periodically have to think about the old knowledge in relationship to the new knowledge. And when it does that, it cleans up a lot of those neuron interference connections. And so what the point in teaching is just to keep in mind, you can't just teach them, chapter 1, chapter 2, chapter 3, and figure chapter 1 and chapter 2 are all perfect, inert, and stay the same way. When you're doing chapter 3, you have to go back and spend a little bit of time reminding them about chapter 1, how this is the parts that are similar and the parts that are different. So that will then greatly enhance this long-term recall. Okay, so I'm going to just stop at this point. The only thing I want to stress is one last thing from cognitive psychology that I study a lot is this idea of working in groups and students talking together. I think from university faculty and so on, they think a lot of that benefit is just from students learning from each other. And in fact, it's stronger than that the brain actually processes differently when it's called upon to teach to somebody else or critique somebody else. It's got sort of these special circuits associated with social interaction, special cognitive circuits. And so the cognitive psychologists can show lots of studies, and my own group has done some of this, where you can take a bunch of students who don't know something, you can test them, you can have them try and teach each other or discuss it, and those same students will come out now knowing and in fact, if you compare a student studying something individually versus interacting with another, like I say, it really kicks in a different cognitive processing that supports learning all by itself. And so it's just good to keep in mind that it's not just teaching each other. There's some deeper things going on there in the brain. All right, so I'll stop with I like to point out when this shouldn't be as necessary with you, but when I'm talking with university faculty, there's always some of them who are arguing, no, this can't be all that bad, because look, we had lectures, and I like to point out to them, they're just not making a proper comparison. They probably would have been much more successful if they had better teaching, but it doesn't convince them, but it makes me feel better. It generates discussion. Okay, so I'm ready to answer questions for as long as Eric wants to let it go.
Thank you so much, Carl. This was a very thought-provoking keynote. And, the chat is going crazy, both here in Zoom as well as on Slack. I was trying to follow both at the same time and listen to you as well. And it hopelessly derailed my brain and showed that, we're not wired to multitask. We can only do one thing at once. There are already quite a few people who are raising their hand, but in the chat, I forgot whether it was on Slack or on Zoom, I think something emerged that I think I would like to hear your thought about. You went from decision-making and decisions to learning. I mean, so much in education is based, and especially in the sciences, is on evaluating things that are either patently right or wrong, right? I mean, you have an object that's 1 kilogram, has an acceleration of 1 meter per second squared. What is the force that was exerted on it? There's only one correct answer. But in many of the decisions, our students, regardless of whether they become physicists or not, will face in the real world is not right or wrong. And most of education is completely focused on evaluating things that can be easily evaluated numerically and made either right or wrong. Shouldn't we also adapt our assessment and our evaluation practices, and not only our evaluation of our students, but even the evaluation of our teaching, so as to create more space for creative thinking and creative decision making?
Absolutely. Yeah. I mean, I should have stressed that more, that has to be, I mean, it's a tremendous failure when you're testing people on these absolute right or wrong. That is just, memorizing procedures, and computers, if the computer hasn't already replaced it, it'll replace it, in a year or 2 years, anything that involves that. And that's what we see with these expert problem solvers is, there's certain things that they just take for granted. You plug in the computer, you look up, but the problem solving, and they have to know about those things as capabilities, but the vastly more important and more valuable things are how they make this decision. And those are I'm hesitant to use the term creative. They're less precisely defined, and so you have to think a little more about them. But, I'll give you an example. We're developing assessments of this that are extremely revealing, and, we can do things like we present, we can present a solution to a semi-authentic physics problem. We've actually done a lot more just because of who's doing what. We've got these more in some engineering and medical situations where you can ask people, what would be, if here's a proposed solution, a proposed design, a proposed diagnosis, what tests would you need to run to check how good they are, and what would be the reasoning behind those? Those are things that we find we can make quite a clean, valid test, but it's also true that they're incredibly revealing as to whether the person's using the reasoning of experts and whether they recognize, they won't know exactly the information they have, but they'll know what information is important in that situation, what information is not important in that situation. They'll be able to know how certain you can be about a conclusion based on these things. And so it is quite a it is very much a different way of thinking about assessment, but I would argue it is absolutely critical and vital and so much more meaningful to give these kinds of assessments. And they don't have to be, look at tremendous creativity. They have to look at, are they using the processes that you would see an expert would follow or not? And everything we look at, there's such an enormous difference between what students are learning in their courses versus what they need to know, that it's plenty sensitive now. The other thing I should stress on this is when we do those assessments across different courses, it's remarkably consistent with they learn what they practice, and so we'll have, I point to a chemical engineering courses we've evaluated, where, okay, 70% of the stuff the students are just terrible at, thinking, proposed design and so on. They'll overlook all kinds of important things. 30%, okay, they're not so bad at. You go back and you look at the course and, oh yeah, they actually practice thinking about, making decisions about that 30%. So it's, there's no great mystery in it, but it is so much more meaningful assessment of what they're learning.
Thank you, Carl, and I think you point your finger on it. It's process that matters much more than just simply the outcome or answer by itself.
Yeah. Yes.
Heidi, you've had your hand up patiently, so let me turn it over to you. Please unmute your microphone.
Yes, thank you. My name is Heidi. I'm a high school teacher in Indiana. And I was just wondering, so I did my master's in education at IU, and there it was really emphasized inquiry-based learning, hands-on project-based learning. But what I feel like I see sometimes is we go to too far extremes in the classroom, where we will do all project-based learning or all inquiry-based learning, and we completely kind of drop lecture altogether. And obviously in some settings, such as this one, it's appropriate and fitting to have a lecture format. Could you speak a little bit more to what you recommend as far as the balance between this inquiry questioning format and still making sure you're getting enough content across to the kids?
Yeah, I think that's a really good question. And the particular content to be covered, there's no real good answer to that. But I'll speak more to the let's say the teaching process, where people go into it's all sort of jumping into this inquiry-based learning or hands-on and so on. You're following, again, you sort of making the same mistake of following a bunch of rules without thinking about what's the design principles behind those rules, okay? And so when I'm working on this or working with faculty, I have them sit down and think very carefully about, okay, what is the capabilities you want a student to be able to have? What do you want them to be able to do? And then think about what's the most efficient and effective way to have them practice doing those things and guiding useful feedback on them. And so, when you talk about when lecture is useful or not, there's some wonderful work by cognitive psychologist Dan Schwartz called "The Time for Telling," and he shows that telling students the same things, or this is a careful cognitive psychology thing, so he's got this prepared lecture, but preparing students so that that's feedback on their thinking. So they've been given a problem to struggle with and work through and talk to each other. Then they get told about it, versus the opposite order, where they get the lecture and then they go off and spend the same amount of time sort of practicing solving things. He gets a factor 10 difference in the subsequent measures of learning, and so that's just stresses how you have to understand that, it's not that talking to people isn't valuable. It's what you're accomplishing talking and how this fits into the, what's going on in their brains and how this is supporting it. Is that brain prepared to learn from that talking? Can it be used as the feedback by which they have a structure for thinking and processing and applying that feedback to go better? Then, lecture's great. Now, if I'm talking to all of you and I don't know exactly what you're thinking, but I'm assuming you're coming in as high school teachers, so you know a whole lot of stuff about this. And so I'm trying to think about what can fit into your existing things and support it. But, if you were all third grade teachers, this would have been a total waste of time talking about. So that's sort of a, give an example. But just to summarize, what I would say is, the best answer I can give is think about what capabilities you want the students to have, and then how are you going to be in the most efficient, effective way of having them practicing that thinking and getting feedback by which they can see how to improve that thinking.
Thank you, Carl. We have a number more people who want to ask questions, so I'm going to turn it over to Marcy. And please, if anybody else who asks a question could follow Heidi's lead in introducing themselves, this way we get to know each other. So Marcy, over to you.
Hey, I'm Marcy. I teach at Ottawa High School in Chattanooga, Tennessee. And my question is really more general about how do you think we can improve access to physics education research for high school students? I mean, high school teachers, because so many of us can't access the journals online.
So I look at it as it's a deeper question than just accessing the journals. It's, because, okay, a lot of the journals are written for, and, understandably so, a whole bunch of stuff about the detailed methodology and statistical analysis that you don't care about. You want to know if it's right. and so, so I'll say I don't know the answer to that. I think, I think this is one of the outstanding issues that we face really kind of as a society. Is we have a lot of new research now on better ways for learning, and it's not getting disseminated. It's not getting effectively disseminated at the level of the teachers, especially at the level of the teacher training programs in most cases, and it's not getting disseminated at to the level of the university administrators and what they should be guiding. And so I have to say I spend lots of time worrying about this, and I can guarantee you I don't have an answer. So it's an important question, though, and maybe things like this are probably better than anything I know of.
So, Carl, there were a couple of, Martha pointed out that the physics education research supplement to physical review is open access, so everybody can access it. And then John Bergman pointed out that on Google Scholar you can often find, but we have people from the NSF here too, and you know, if there's a real need and a problem for people in high school to actually access the professional journals, then we could put our heads together during this week and see if we can come up with a solution. So thank you so much, Marcy, for raising that issue.
But I don't think the question, ultimately, I don't think the fundamental question is accessing. I mean, there's things that could be done, it could be done better, and there are more and more open access. But I think fundamentally, it's not just seeing the research journals that's the problem. So
right, networking like we do here is another way of doing it.
That's right. And the NSF has struggled with this a lot because they've supported a lot of programs being developed things, and they just haven't spread to the teaching community.
Well, one of the goals of this week's meeting is precisely to facilitate networking and connecting higher education to high school education. A lot of hands went away unless I accidentally hit the clear all button. I don't know. So if you see your hand is no longer up, please raise it again. So I see that Maksuda Afros has a question. So I'll turn it over to you, then Andre, and then Doc Roth. So Maksuda.
Hi, first of all, thank you so much. That was an amazing talk. It's an area that I've often struggled with. So one thing I do for my students is I often start off with simply, which way does the sun rise? And of course, they all tell me it's east. And when I ask them why they say that, most of them end up saying because their teacher told them so. This is something they learned, right? Like teacher told them so. So then my next immediate question is, what if I told you it rises in the west because I'm more experienced, I'm more thing, would you believe me? It gets the kids completely confused. And that's how they really get into like, okay, I need to actually prove a statement instead of just taking it from a book or a teacher. My problem is because students are so used to lecture-based learning and knowing the teacher knows it all, how do you give them the confidence to actually become the driving force of a lecture? Like, is there a methodology to be able to go there? Or, because that's the piece that I struggle with. Like, how do I give them that confidence to say, okay, it's okay for me to be wrong and still drive the lectures?
So I can't give you the answer for your students. I can give you the answer for students that I am familiar with and worked with. And that is that we, which is kind of different levels at the university, but I'll focus on first year. We have very much the same issues that you describe. And the only way we seem to deal with them is to be very explicit about it, about how we're teaching you in a different way. We're providing you with a different new set of skills, and that, arguing, discussing with each other and putting forward arguments is the goal of the course. It's not about remembering and memorizing and having a specific, correct thing. It's the process, it's the discussion. And so in that case, we make it a very, very explicit discussion about how they're learning something new, different. And it takes a little while, but we also give them, it really helps to give them some, I won't say easy, because none of these are easy in some sense when you haven't done it before, but things we be pretty confident they can be successful on. And, and over time where they see they can be more successful, and we kind of focus on their success, and we focus on their success at the process, and keep coming back to this idea of, no, what we care about is the process, and, and discussing, well, that isn't the official explanation, but here's the really good aspects of how you reason through this, as opposed to, no, the answer is F equals MA. That's what we've seen happen. But it really, the advice I can give you, and again, I think it has to be matched to your particular student population, is that it has to be dealt with in a very explicit way. of don't just assume they can get it. You have to talk to them about now they're learning something new in a different way than they have before. And, you know, it's going to take a little while for them to get into it. But one of the benefits is it's so much more fun, right? So, you know, once they're given a problem in which there is no right answer, I mean, that's the really good part. Give them a problem in which there is no right answer, you know, and they get to talk about what possible answers could be when you've very carefully chosen it, so there isn't any right wrong. That goes a long ways towards sort of we've seen in changing their attitudes.
Thank you.
Thank you. Do you want to follow up with another question, Maksuda?
No, like I was just gonna say, like I definitely agree, because half of my questions will be based off of that. Like, what would happen if we did something which there's just no way of guessing, and then have to kind of sort of maybe not. So I'm just saying, like, I agree with you totally. Thank you so much. Appreciate it.
I mean, sometimes people talk about this in the education people and other direction of cognitive psychology of productive failure, of giving things where you know the students can't come up with a right answer. But, you know, and Eric can probably talk a lot more about it because, you know, he's switched to this kind of project course where, okay, there is no such thing as a right project and a wrong project, right? So everybody's thinking of different ways, and that's that becomes the entire point of the course, is thinking of different approaches, not coming up with a right or a wrong thing.
Thank you.
Yes, and I will touch briefly on that when I speak on Wednesday. Before I turn it over to Andrei Yarczynski, people have already started making tables on Congregate. There's one table devoted to smartphone labs, one to physics education research, learning about learning, school reopening. There's still the one that I made on modeling, but I'm going to delete that because that came from me, and that was just an example. So please make up your mind what you want to do over lunch. And there's this channel on Slack called Lunch Break where you can see if there are people who are interested in joining a table to discuss a subject of interest to you. But we have a few more minutes left in this session, so I'd like to turn it over to the next person. Andrei, please introduce yourself. I mean, I know you, of course, but you want to introduce yourself to the audience and unmute yourself.
Okay. Hello, everybody. I'm Andrei Yarczynski, and I teach physics at Boston College. And thank you very much, Carl, for this talk. I am a bit of a convert already, in large part due to Eric's work and his book. So I'm quite convinced. But I want to return to the question Heidi asked some time ago about the balance between these new techniques and the regular lecturing. And it's something that I've been thinking about for a very, very long time. And I do include, Eric, please don't be horrified, but I do include some parts of regular lecturing. And my reasoning, and that's what I want to ask you about, is that there are certain things that have value in becoming a physicist and being a physicist, which are not really capabilities or skills, and are not easy to measure, if at all measurable. And basically the culture of doing physics. And you know, there is this book by Weinberg about, what is it called? Exploring the Physics or something like this, and how we had to learn what physics is and how big an effort this was. And I think when you do a little bit of regular lecturing, if it's well selected, it conveys not just, it illustrates not just some skills in the way you're doing things, it's the way you talk about it conveys culture. You know, I've learned a lot. My father was a mathematician. I learned a lot from him. I think about my teachers in university, and I remember their style. And you know, there's this genealogy project where mathematicians trace who they were taught by and so on. So I'd be interested in your comments whether there is something that's conveyed by things other than, you know, having concept questions with clickers?
So I'll go back to the answer I gave before, which is I think that, you know, sitting down and going through how experts solve a problem to somebody who's not already pretty much of an expert. And I would guess that in your case, you came into the education system in some sense pretty expert in thinking from your interactions with your father, okay? And my guess is that didn't happen because he would sit you down and give you a 3-hour lecture every morning. It was discussions back and forth. But for most students, the majority of students who don't come with that kind of, let's say, cultural preparation, I think these kind of explanations of process simply don't mean anything. And so, so again, the issues, and I'll fall back on the work I talked about with Dan Schwartz and this time for telling, how he shows such a big impact of having the students first try and solve a problem. Okay, so that's, you know, that he gives them the preparation for for the learning from the telling is by giving them a carefully designed problem, which is, you know, in many ways a very much a toy problem, but it's got realistic, that toy has realistic elements of what factors you need to be thinking about, what things you need to be taking into account in some ways in a much more scientific way than is normally conveyed. And so they've already been sort of thinking about, oh, I need to figure these kinds of things out. Then if their brain has been sort of adequately prepared for that, then these lectures about process mean a great deal more to them. So you know, that would be my answer, is that I have yet to see anybody show data where, you know, they're taking sort of a random, fairly unknowledgeable group of students and having them learn very much at all from the lecture. So I think even understanding when you're talking about the culture, I see that as, I mean, I agree, there is a culture, but it's a culture of process there. And I don't think people can well, I'll make a stronger statement that you can open the newspapers every day and look at, you know, politicians and the decisions they're making to realize that that process is totally foreign to much of our society. And so until you go through a fairly careful process of developing that in them, and the lecture is not a lecture providing the first new information to them, it's a lecture supporting and building on their thinking and preparation, you're going to be more effective. So
Thank you. Thank you also for that question, Andre. And no, I'm not at all shocked. And of course, I still lecture, and we all still lecture in various cases. The thing that you might ask yourself, which is something that I started asking myself much more as we went online, is to what extent do you want to use synchronous time for lecturing? And I sort of have a saying in my mind the whole time, resonating in my brain the whole time, that says, if it can't be recorded, it should be recorded. And of course, any interactive activity would be very hard to record because you can't participate. So the person who watches a recording of students talking to each other, or an instructor and students talking to each other, is sort of a, you know, shut out from the interaction. So that might be a way of still doing lecturing, but not taking the synchronous time to do that. Carl, do you have time for one more question?
And you know, Andre, the other thing I'll say is, I mean, the people who I've been the most impressed with the results they get in sort of coming into this field is always talk very much about they talk about lecturing to the students, but they always talk about making sure the students have been prepared for the lecture. You know, the student brain has been prepared for that lecture, and I think that's sort of a way to think about it. Yeah.
You have time for one more question,
Sure.
Carl?
Yeah.
Okay, and again, I see quite a few people have made tables and joined tables, and again, you can just jump from one table to another by clicking on the different tables later on as we break in a few minutes here. So, Doc Ross, over to you. Please introduce yourself briefly. I know you've already been on the screen, but I don't think Carl was there when that happened.
But Carl and I did meet at Tufts a year or two ago.
Okay.
Joshua Roth, a physics teacher at Arlington High School in the suburbs of Boston. I just want to, this is not something I'm asking for an answer about, but something to throw out for everybody, and it could be another table topic or another thread. One of the things I struggle with, and it relates to a couple of things here. One is when you bury old learning with new learning and you only have a little working memory, how do you set things up so students, learners can reactivate the older learning? People use terms like spiraling. And then the other thing is, in the terms of lecture, people really react to stories. And coming from journalism, editing background, I always asking myself sort of what is the narrative arc of a lesson, of a course, of a unit? And if you can somehow turn that maybe into a visual, a graphic organizer, a concept map, something, then I'm wondering if there's an opportunity for students to have a structure on which they can put these different discrete skills or contexts. In physics, it might be kinematic graphs. But then you go on to energy and you're not thinking about kinematic graphs, but when the test comes, you have to do it again. And plus you would like to have general skills with graphs of rates and quantities. But also a way to customize our teaching and have it addressed to our communities and the different students and the different, and their interests. Sometimes I got a room full of kids into sports, sometimes artsy kids. I mean, everybody's everybody, but there's, you know, but while still invoking those same core things, which are standards based on the frameworks, on the standardized tests, the state gives, and so forth. I'm just curious what other approaches people use to construct a narrative, to have a framework, so that as the kids learn, they see how the discrete skills they're getting fit into the whole, and also have a way of going back to those and re-looking up, re-accessing them when they need them. No response required at the moment, but this business of narrative and I think it's worth unpacking. Well,
so, yeah, so this is a much too big a question to answer, so I'll leave it for lunch and table, but I'm just going to touch on one tiny little piece of it where I think I can answer it, which is that the example you gave about, you know, using kinematics and then you go on to use conservation of energy and so on. There's really no issue with the short-term memory at that point, because you're dealing with stuff that's in long-term memory. But the thing you do want to do is just not keep them as completely separate. That as you're doing the conservation of energy, you want to spend some time having some problems, some examples where they have to decide which of these techniques is going to be useful and why, okay? And so that's what you want to keep regularly doing is, you know, and sometimes it's going to be the method has no relevance whatsoever, but just having them spend the 3 minutes thinking about that and recognizing that there, what relationship there is or isn't is actually quite valuable. So that's the easy part of the question. Okay.
Well, thank you so much, Carl, for your time, your generous time and wisdom that you shared here. We all greatly appreciate it. There'd be a thunderous applause if we were in a room together. Failing that, we have the virtual applause here. So thank you so much again.